the amplitude increases and also the duration increases. But not only that, the frequency content is also different. For a smaller earthquake, we have a short period like 0.1. Then for bigger earthquake, we can have 2 or 3 seconds period. So it's not that amplitude increases, duration increases, but also the predominant period also increases. Means more damage, they say, to huge structures. About the directivity, this is one of the earthquakes that occurred recently. And in this earthquake, you can see that this is the fault, the red one over here is the direction of fault rupture. Then most of the damage and the high frequency, the high intensity recorded along this direction, while on the side, very close on the side, there isn't much damage. So the direction of rupture is also another important. The distance, it attenuates with distance. I just took one average curve from earthquake. So with distance, it reduces. This is very obvious. Energy is lost as it goes. Then the earthquake magnitudes also affect the predominant period. Why I'm repeating the predominant, as most of you know, it is the coincidence of the predominant period in the earthquake coincides with the predominant period of the site and the predominant period of the building. This is a disaster. It is what we call high amplification. This is called resonance. So always we should be very much aware of the predominant period in the earthquake itself, the soil and the building. Because the building is, the structure is in our hand. When we design, we have to mismatch from the means, make a distance. For example, if we have a long period, like in the Mexico City, earthquakes come from far distance. The soil is very soft. So it was, the source was about 2 seconds in the earthquake. The soil, the lake bed in Mexico was around 2 seconds. Then mostly between 18 and 25 stories were damaged. So we can play. Even if it is 20, we can frame it and reduce the period, or we can make it more flexible and elongate it. So we can play with this. So we have to be aware of the trick. So when we come to sites, we have 2 things to be considered or worried about. The first is the gross instabilities that occur. This mainly occurs in the form of liquefaction, which it could be gross liquefaction, like in the Anchorage, Alaska, 1964, or it could be the cyclic mobility. Same year, coincidentally, 1964, again in Niigata, Japan, it's caused by cyclic mobility. It is about the effective stress more than the cyclic stress or not. I think the detail most of you know. But liquefaction occurs when the soil loses its strength, when the cyclic stress, the dynamic stress generated is more than the effective stress. In any case, the 2 occurred in many places. They cause damage. This is gross instability of soil. Then there is landslide, which is induced by earthquake. There is settlement. Settlements occur, especially groundwater material settle significantly. Then there is ground rupture, which is not only a fault rupture, but fault rupture is there, but also ground car rupture if it is weak due to the high strain earthquake occurs. Ground could rupture outside fault areas. So these are gross instabilities. They are treated differently. For liquefaction, of course, we can densify, we can avoid the site, we can use piles and so on. Landslides, we can design, we can change the slopes if it is natural slope. We can design, it's fine. Settlements also we can consider. Ground rupture, if it is a fault, I don't know until now any engineering solution for fault rupture by exactly on the fault. It's this Friday the 13th. But if it is a small rupture, we can avoid by densifying by some designs. The second aspect of ground effect is the site amplification. Means a given shaking comes to the sites and it is amplified or de-amplified. It's not amplified, but sometimes it is de-amplified. High frequencies could be de-amplified on soft soil, and low frequencies could be amplified on steep soil. So both, but we are more worried about the amplifications that may occur. Sometimes it's 2 up to 3 times the ground shaking could increase, or the peak acceleration, peak velocity could increase up to 3 times due to ground effects only. So these are some examples. So this is as the soils are softer, this is the shear wave velocity. Then the red line shows stiff soils amplified, let's say up to 2 times. At least in this case, these are earthquake studies, not hypothetical. So soft soil for the same earthquake, it's recorded for the same earthquake. So this amplification is about 2 times for soft soil. This is for the same earthquake in the same area. Actually, interestingly, in Mexico City, the lake bed was destroyed, the center of the city. The National University of Mexico, which is close by, on a rock, nothing happened. So I visited the site as a student at the time. Then we visited the site, so nothing happened for the university. Not because they're educated, but because they're built on rock. This is also from Loma Prieta, the famous 1989 earthquake 6.9. So this is a rock site. You see it here on bedrock. It is very small. Then on soft soil, and then on stiff soil. So this, for the same earthquake in the same area, depending on site, there are different amplifications. Then having said this, finally, when up to the ground motion, we are talking about hazard. The soil is in between. It falls in the vulnerability along with building. Sometimes people use vulnerability for building only, but side effects should be added. It's not a hazard. Hazard is up to ground acceleration. The soil amplifies or de-amplifies along with building or any structure. This falls into the vulnerability. So the seismic risk is seismic hazard times the vulnerability. Seismic hazard, job of seismologists and so on, the vulnerability. Our work, then together we evaluate risks. Another important aspect is shaking occurs on the ground. The most devastating is the horizontal. This is the shear wave velocity is the main damaging, but surface waves also, lava waves, which also act like a shear wave, but in the horizontal direction, in the 90 degrees azimuth from the surface wave. Also the Rayleigh wave, which goes in elliptical way in the ground. So this is, we're not much worried about vertical components. We're not much worried about P waves. We're worried about surface, the body and surface waves in horizontal setting, because buildings are very weak horizontal, and that's where the damage comes. Okay, we use the code method. This is just one example of the code method. It is the equivalent lateral load method. I'm not going to discuss about that. I think every engineer is aware about this one. It's okay. The importance factor, some spectral acceleration, behavior factor are considered. But truly speaking, just in one word, maybe we can raise in the discussion, very little is done to save building using the equivalent lateral load used in codes. At least we have to add other things. It is, first of all, this is based on force. Earthquake is an energy. It is not a force. Engineers like force, so we always try to say, yeah, we force times acceleration, force times mass times acceleration force, and so on. It's easy for engineers. We like force, but we are dealing with energy. So in earthquake, energy comes to our structure, and it is either dissipated by elastic or inelastic movement, by friction, by other means, or it is absorbed and it tries to get out by cracking our building in the inelastic range. So if we understand that it is energy, it is much better than this. I don't mean it is zero, but so often buildings designed by code did not survive. Of course, other factors, construction, quality, understanding, it does something, but only if we incorporate energy dissipation, but with good ductility design. Otherwise, it is just an approximation, does not exactly coincide with earthquake. So if we go to, I'll go a little to now to the side effect. To go to the side effect, one of the important things is we must determine the strong motion we use. we can use different instrumentation. The best is to measure. If lucky, for example, we are in Accra, then we have strong ground motion recorders. We have done that for many years, and we know our ground motions that are statistically, then it is the best. But neither California or Tokyo has that, because the strong ground motion recording is recent. Even Japan did not record the 1923 earthquake, or America did not record the 1906 strong ground motion, because at that time their seismometers, they're already saturated. So this strong motion recording is good, but we are talking about return periods of, let's say, 475 years or 1,000 years, with a probability of exceedance of 10, let's say 50 or 100 years return period. So we don't have the record. If we have, that is good. But no country has that, no site has that type of luxury. But as we go on, recording strong motion on sites is good, but that will be from X fault. How about another earthquake from fault Y, fault Z? An earthquake in one place can occur from 10, 20 different fault zones. Therefore, that recording will maybe after 1,000 years, people are recording now, but for now, it's okay, it helps, it's good, it is on site. But whether single, worldwide, regional, local dense array, or vertical arrays, it is good, but we cannot have appropriate for a site fully. Then, of course, when an earthquake occurs, there will be different waves, P converted to S converted to S, surface waves, and so on. There are 6 components: horizontal, vertical, horizontal 2 directions, and also the rotational. Often we are interested on NS and EW. The rotational, we don't even, only for scientific purposes. And we're focusing on S and surface waves, though we record waves naturally. So if we record, the NS component is, for example, the one at the top. Then there is the vertical component. Then there is EW component. Why aren't we interested in the vertical? The vertical shows usually the P waves, which are high frequency and out of range of damage of building frequencies, building design buildings. So as you see, the S waves are very much reduced in the vertical component. So our interest is in the horizontal components, which amplifies the S and the surface wave. The P wave is 0.1, 0.2. It is out of range of most buildings. What are we interested in? If you want to make, now I'm trying to build a case to dynamic analysis, not the code method. So so when we record strong ground motion or generate or whatever, we are interested in the time history, in the peak acceleration velocity displacement, and effective sustained acceleration velocity on displacement, not the whole range, but on the effective one. Then the frequency content parameters, the Fourier's power spectra and response spectra, the most important. Then spectral parameters, bandwidth, central frequency, shape factor, duration. So these are what we're looking for dynamic analysis. Actually, when we talk about peak ground acceleration or acceleration records, peak ground displacement, velocity, sorry, I'll correct my PowerPoint, is peak ground velocity, PGV, and the peak ground displacement, PGD. We like as engineers PGA, but PGA is a force, it leads to force, but earthquake is not a force, it is an energy. Second, it is a filter for long period motions. It is only usually shows strongly showing the high frequency of short periods. So our buildings now, we're building high-rise buildings, dams, and so on, bridges. So the PGA is okay. With this weakness, we can understand and use it. Let me go to the peak ground displacement, the third one. Peak ground displacement, it shows high frequency and adversely filters the low, high frequency, and medium frequency means low period. And it is only for low frequency or high long period. So the best one representing an earthquake is the peak ground velocity, which I mistakenly called it displacement. Why? First of all, it focuses, it catches something of the short period, the long period and focuses on the medium period, which is what most earthquakes and soils are. Second, it is velocity. So you can easily convert it to energy. Kinetic energy, very easily have mv squared, even simply with our understanding. So if we design by energy method, which is now developed, it's not into course, but which is developed, then we have better understanding, because earthquake emanates energy into our building. It adds energy to our building. So our design should be how to get rid of that energy. For example, by elastic movement without cracking, by friction energy, by dampers. That's what we call dampers, and so on are energy dampers. So this is becoming very common and very appropriate for earthquake. We can use the other ones, but that is more appropriate. How do we get our strong ground motion? Earlier, I read local strong ground motion records. If we have that, is the best, but we don't have all the time. Generated, we can generate synthetically, if we know, or by deterministic seismic hazard analysis method. If we know our fault, if we know the path, like the source, the fault area, the inclination of the fault, and so on, the characteristic of the rock as the fault, and if we know the distance, between source and our interest, or structure of interest, the soil type, where at least roughly in geological terms, rock, soil, and so on, we can develop like Green's function for the path, and we can generate an earthquake from fault and path. This is RDS. It is not that accurate. It has a lot of assumptions. And also, if you do for one fault, there is another fault, and so on. So all this did not make it very famous, but really is a good method, simulation or generation. The other one is blow up medium and small earthquakes. We always record, even in Ethiopia now, you recorded hundreds of small earthquakes. We can scale up these earthquakes and we can use them. The only problem with small earthquakes are short period ones. So as a short period, they don't represent, they don't have long period in them or medium period. So we have to be aware that they don't represent all frequencies, but we can scale up. The most used method is use of previous records. This is the most common used everywhere. We have to be, it's not an African issue, it's not highly developed science. In Japan, in America, in highly developed seismic research areas, this is a method that is often used. Use of previous records. How do we do that? There are some records which are very famous now in the world. All over in Ethiopia, I'm using for my designs. In Japan, I have practiced for some time. We're using that. I've visited some universities or design firms in the US. They use this. For example, some has shown very good characteristic, the 1941 El Centro earthquake. This earthquake is recorded in Pereira Valley, 1941. It is like short period earthquake, the one shown on top, the frequency content shown on top. What we need to do, I have done that. This is the soil at El Centro site. This profile, what you see here. So you have to deconvolve it. You have to make an inverse analysis. Usually, we put the ground motion at bedrock and calculate the response on ground. But in this case, as El Centro is recorded on ground, it is the same. It is the same. For example, for this, I used Shake, very simple program available anywhere, even in the internet. So with this, it is deconvolved to the bedrock. We have to take out the side effect of El Centro. Then the deconvolved motion looks like this. The spectral, the acceleration response spectra looks like the lower one. So this could be used at another place. But it has to be scaled to the peak ground acceleration of from the hazard analysis, for example, for Addis, for Abuja, or for Johannesburg, wherever, Cairo. We have to, we can use this one. It represents a short period. Okay. Another earthquake. The Kern country, Taft 1952. This medium period. The same thing is done. The Kern soil, it is deconvolved for the Kern soil to the bedrock. So mean side effect is taken out. So we can use the deconvolved motion, but we have to again scale it. Another one is the Hachinoe Tokachi earthquake 1968. This is the one I said it was almost at zero. So it has a lot of surface wave. It's long period earthquake, about 2.2. So this is also deconvolved for Hutchinson sites. Then the spectra looks also the lower one. I plotted both together. The other earthquake that became currently famous since 1995 is the Kobe earthquake. This one, it is the earthquake occurred just under Kobe. That's why it was a lot of damage. It was 7.2, but it created a lot of damage, more than about 100 billion worth of property. And for Japan, 6,700 people dying is very serious because I believe they have done a lot in earthquake. However, this earthquake is also deconvolved with the Kobe soil. So this is one available earthquake. So if you use the four, the El earthquake represents short period. The Taft earthquake represents medium period. The Kobe earthquake represents, you can see from the frequency content, it is like a bomb. It is between 0.5 and 1. It is a flat. So another earthquake. Then the Tokachi Oki earthquake represents some short period, but also long period, 2.2. So with this, we are trying to cut difference frequency. Up to the amplitude, we will somehow calibrate it to the strong ground motion from the hazard analysis. So this way, you can add another one, but these are the common methods. It's not only, the four are not only different in terms of amplitude we manage by our period, but also the energy. For example, this is a simple analysis to effective duration is calculated from the 95% energy it should be explained. So the 95% energy is explained for El Centro in 23 seconds, for Taft in 32 seconds, for Hachinoy in 44 seconds, and for Kobe in 9.8 seconds. This is effective. So they also represent different effective durations. So this way, this record is available. I can upload it. The deconvolved one, you don't have to go through deconvolving. This could be used by, I'll submit to the association. So Engineer Emmanuel, anybody can use it judicially. So this is, then we go to site analysis. The first thing to determine where is our input. So for example, if our structure of interest is here, we have to input the ground motion, the deconvolved ones, the peak acceleration adjusted ones, peak up velocity or peak displacement at the bedrock. So this is one, we have to locate. If you are making an inverse analysis, it's possible also, but often we have to put it, these earthquakes or others are bedrock, so we can do the propagation. So the soil should be, we have to determine the soil properties, the thickness of the soil, the density, unit weight of the soil, then M layers, so these are the damping and the stiffness characteristics should be characterized to make dynamic analysis for site. So quite simple. Geometry, this is only one-dimensional analysis, but if it is a valley, we have to make a two-dimensional analysis. If it is a basin, we have to make a three-dimensional analysis. There are softwares like Flash or commercially, there are also other softwares. So, but just for our case, I'm using a linear, one-dimensional analysis. So the earthquake input is, so we define each layer with thickness, with density, with damping characteristic, and with shear modulus characteristic. Then we can make the analysis easily. So what do we get? So the strong ground motion is input at bedrock level. Here, input motion. Then this is the time history. This analysis based on, by the, okay, for the analysis, we can use time history analysis or spectral analysis, spectral modal analysis. It's okay. We can use both methods. So in this method, I'm referring to the ground response analysis, not with the time history, but with modal analysis, spectral modal analysis. So the first thing we have to do is we have to convert the input motion at bedrock level to with use to inverse Fourier transformation with fast Fourier transform software or anything you can. Then we have the frequency domain. This is a frequency domain analysis. Then we have to, from the soil, which we saw earlier, all these parameters will give us one function, which is called soil transfer function for the different frequencies, for the different layers, and for the different periods of frequencies. Then if we can determine the site transfer function, which is very easy, by the way, it's not a big deal. Even you can do it by hand. T is 4h or VS over 4h. You can calculate, but can do with software. In frequency domain, the multiplication of the input motion times the site transfer function will give us a surface response in frequency domain. Then we did Fourier transformation. Now we make inverse Fourier transformation and we get the time history at surface. The geotechnical engineer's job is finished now. You can input into our foundation and calculate. But also we can use this bedrock, model the soil along with structure, and also design. But this is good to design this way, makes the site analysis and understand the time history or the frequency domain characteristic at surface is more important. Even if we do the overall modeling, we have a feeling for the soil this way. The other is we said we need two parameters. That is the degradation in shear modulus, the stress-strain relationship, and the damping. So for static, we have one line, then we have Young modulus. Okay. Here we have two things. Mainly we are dealing with shear. So we are interested in shear strain and shear modulus. So in earthquake, we don't have a straight line. It's not reversible on the same direction. So we have a curve. So we have to determine the shear modulus. Theoretically, for dynamic analysis, the shear modulus is infinity. At each infinitesimal strain level, the shear level, as you may see, it is changing. But we can take an average for one cycle. The damping curve is similar. The G over G max, we can normalize and get this one. So this is what is a test for dynamic shear, traction shear test looks like. This is only one cycle. First, we have this one, it goes up, then it returns along this direction. Why? Because there is damping. This represented this area that is lost between this and this is damping. The slope of a curve is the shear modulus. So this is for one cycle, we can take the average shear modulus. This is the second modulus. But we can calculate for each infinitesimal distance and program, but a lot of assumptions occur. So one cycle, 1G, and one damping ratio could work. Then similarly, we do a number of cycles, then we can get the shear modulus for each. The shear modulus, it is degradation, it reduces, the damping increases as the soil gets weaker. So these are represented in this manner. For example, this is the damping, which increases with, let's say, with more strain. And this is the shear modulus. It reduces with as strain increase because it cracks. It is a strength parameter. It reduces. The damping increases. So this is what we get if we plot the one hysteresis slope at one point. There is something to it. Then if we plot many hysteresis models, we can develop a simple curve, G over G max over G, so G over G max versus strain and damping ratio. So we can use equivalent linear method. If we are not very familiar with to use these curves, model them, write the equation and use them, we can use the equivalent linear method. It means for example, we assume a small strain. Then for that small strain, we get 1G and one damping. This is from soil tests, but now it is standardized. Like seed and debris engineers, old timers did many curves in Japan. It was added by Goto and by Ishihara. Then now there is some average curves in these aspects from many earthquake records, so we can use the equivalent linear method. Then a new strain is calculated. Then with a new strain, we come to another G and so on. So this way we can use the equivalent linear method if we are not using the full dynamic. So the basic things are seismic analysis, design structure, time history record is required. Time history is over not available. You can use like recorded elsewhere motions. Peak values do not catch frequency content, so we have to be aware of the frequency contents. Max, the velocity method, using velocity is good, it's energy method, but displacement could be checked separately because displacement is another factor. So in earthquakes, response spectra, the motions and response spectra are related. The other is so to solve this halfway, for example, the soil characteristic, we're not using dynamic, we're using the response spectra. It is a dynamic analysis, but we take a single degree of freedom system with different periods, T1, T2, T3, T4, then strong ground motions, and we calculate the response. And this is how we get now the response spectra for single degree of freedom system, or even for multiple degree of freedom systems, as you may see here. Then with that, we develop the response spectra, which comes to cores usually. Then these are analyzed statistically, average is taken. So every core develops now its own response spectra based on this method. This is the code method, but at least some dynamic aspect and ductility, energy dissipation is considered through the response spectra. I'll come now to the East Africa. I think I'm running short of time, but I'll be fast. Then in the East Africa, well, three plates are mainly responsible for the big plates are the Eurasian plate and the African plates, but subplates are Arabian plate, Somalian plate. So in the North Africa is the African plate, as you may see, is moving upward, and the Eurasian plate is moving down. So this is creating a convergent boundary. It's the creation of the Atlas Mountains, the mountains in the Maghreb area, and so on. All these are cause of these two collisions, and this generates one of the earthquake, like the 1917 Algeria earthquake, Ansam earthquake, and so on, and the Cairo 1990, so many other earthquakes in these areas generated by this collision. Then the East African system is the Arabian plate. The African plate moves upward. This Arabian moves up, but with different frequencies. That's why with different rates. So that's why we have earthquake in the Rift Valley. Then when it's starting with Ethiopia, it comes inland. Then it is the Somalian plate is moving on. At this point, it is a triple junction. It's a triple junction, Arabian, African, Somalia. But once it enters into the territory of Ethiopia, after some distance in the Afar, it becomes the Somalian and African plate moving apart. This has been happening starting with Holocene at least 50 million years. So it's moving at a rate of maximum 2 centimeters per year, but on the average from 0.5 to 0.8. As a result, the East Africa has generated many earthquakes. So this is a plot of the earthquakes shown here. A better picture is, this is what the African continent looks like. Actually, the rift system, by the way, is the north margin in the south. This is the north margin with the rift, with Ethiopian rift system. Then there is another which is off-center, touching, like you remember the Juba earthquake, which was 7.2. Then it goes to southern Central Africa and Southern Africa. South East African earthquake systems through to Malawi and also South Africa and Southern Africa. The North is it, but do not eliminate. There are earthquakes in Central Africa, as you may see. There in West Africa, around Cameroon, Ghana, Nigeria, there are earthquakes. So frequency is less, but the earthquakes occur. Sometimes big earthquakes occur in these areas also. So these are magnitude 6.8 and above earthquake in the last 50 years. So you can see they concentrated, but also you can see how they occur offshore in Western Africa, which could cause tsunamis also. Offshore here between Madagascar and Tanzania and Mozambique, then it can create also tsunami. So there are big earthquakes occurring not only in the rift, but out of the rift also. These are some of the earthquakes. It is a study made by Alaname and et al. So it is not an overall record, but for zone North Africa, they have recorded between 1970 and 23 earthquakes. 7.3 is an Ansam earthquake, which is very famous, 1970, was a lot of damage. But this is not comprehensive. There are many other earthquakes, Algeria, even Morocco, Agadir earthquake. But it gives this, I thank the study made by Alaname et al. There's also some earthquakes in the Central Africa. It is occurring. So we have in the Southern Africa. So for example, like Nigeria. So there are earthquakes everywhere. In Ethiopia, it is concentrating in this area. We have the plates here. The three plates meet here: the African, the Arabian, and the Somalian. So this creates some dome-like motion, triple junction. Many earthquakes occur in that area. Then it goes through Ethiopia to the southern part. Just for an idea, in the last 100 years, there are 16 earthquakes above magnitude 6.5 occurred. This is like the type of, this is between 1886 and 1990. So adding the recent ones wouldn't change much because mainly they were less than 6.5. Then the recent earthquake, which has created alarm, it is a little strange phenomena. This is, okay, interesting phenomena, not strange. Nature is always not strange, actually. So this earthquake is enormous. 94 earthquakes occurred above magnitude 4.8 in a short span of time. There are 43 earthquakes above magnitude 5 between September and today. So it is sometimes in one day, 3-4 earthquakes occur. So this is the frequency. Mostly it concentrates around 4.8. The focal depth is 10 kilometers. This is caused by, with the preliminary information we have, from the volcano, but not volcanic eruption. The crust in Ethiopia, the lithosphere is very thin. It is around, in Afar areas, some people say it is between 15 and 20. It's not like 35 on the average for other areas. It is very weak. It has been under tensile stretching for many years, so it is very weak formation. So this very weak formation, the astronosphere, which is a molten magma, is always moving, of course. The tectonic earthquake occurs due to this movement of in the astronosphere, which is semi-solid, which creates when it's melted with a lot of temperature and pressure, which melts to magma. Then this movement creates tectonic earthquake. But sometimes it erupts and comes to the ground as volcano. So volcanoes and seismic areas coincide, especially in tensile stretching zone. They go side by side. So the current phenomena is first of all around 10 kilometers. The magma has come to 10 kilometers and starting to push and come to the ground as a dike, not as a volcano, as one event. It is coming up trying to separate the dike around 10 kilometers to stop that it is trying to come out is what is causing these earthquakes continuously. This is a curve which we see here. So you can see over nearly 100 earthquakes occur above 4.8. If we count other, it is in thousands. And still, it is not stable. The good thing is energy release. A given fault has certain energy. When energy is released, it doesn't mean it is bad. It is means ultimately it is the same amount of energy. Of course, this strange, it occurs in an area of 180 kilometers apart between Dauphin and Fantalle. It is fault is clearly seen on the ground, so it's occurring in a far distance. However, we don't like earthquakes, but it is better if it occurs in small bits rather than one big earthquake, but we cannot rule out a big earthquake. These are the damage which you see everywhere. This is from this earthquake. The damage is not only a function of the earthquake. It is also the function of how good we build. So I have no assessment of most African countries, but I have visited some countries. The situation in Ethiopia could be similar for most African This is actually this occurred due to 5.2 magnitude earthquake in an area called Kasam. In other places, it's not supposed to cause any damage. Just one example, in 2011, 3 earthquake occurred, interestingly. In Haiti, it was 7.2, 2 building was entirely damaged, and 230,000 people died. In Christchurch, New Zealand, a 7.2 earthquake occurred, but 5 people died. In Chile, the same year, an 8.2 earthquake occurred, which is about 40 times more, about 31.7 times, sorry, more energy compared with Haiti, but only 525 people died in building. Of course, the Chillers were a little far from population destination. However, this can give us an idea. It is how good we build. Damage is not a function of the earthquake only. So it caused many damage. These are also other seismic events. This is the 1961 earthquake, magnitude 6.6. It damaged Majete, Karakore in Ethiopia. It's also along the Rift Valley. So just some old pictures. This is a 1969 earthquake, magnitude 6.2, but there was a town at that time, a town called Sardo. It was fully damaged except for this telecommunication wood structure and one water tank. The casualty was 50%, deaths and injury. So everything was flattened in the city except these 2 structures. So small earthquake can cause this. In Ethiopia, a magnitude 6.8 earthquake occurred in 1906. It was felt in Addis. Addis was, unfortunately, in Addis at that time, it was not well built. So this could be the same for many African countries. Earthquakes occur, but we didn't build much. Now we have built high-rise buildings, dams, many structures. We have moved to close to seismic areas, and towns have come. So just a scenario for Ethiopia is if the 1906 magnitude 6.8 occurs again, now we have a different picture, not like 100 years ago. So we need more preparation, and we have to prepare. So it's not we're not prepared. We have a code. I don't want to go into code. It is uploaded. You can refer to it. We have the 9814. It is an adaptation of Eurocode. Ethiopia, we are adapting Eurocode, and because we don't have enough research to do everything, so Eurocode is prepared. I'm not promoting Eurocode. It's my rational, our rational how we chose that. Eurocode is prepared considering 28 countries in Europe, with highly technologically developed countries like Germany, UK, and so on, France, and with other less advanced knowledge in technology or in engineering or in seismic areas. Different economies, different way of building. So we consider ourselves like the 29th country, and we took that as template and we adapted. So we have that code. It is equivalent to static based method, but it's suggested as clear. It says, if your building is high, important, irregular, horizontal and vertical, you have to go to dynamic analysis. Clearly stated. For simple buildings we can use, but considering the response spectra, so that way we can touch some of the dynamic aspects beyond the elastic range by ductility and also by some dissipation, energy dissipation mechanism. So the code requires no collapse requirement. One, means some structures should not collapse, important structure, hospitals, and so on, even in an event of earthquake, they have to serve in the aftermath. Damage limitation requirements, since we're referring to maximum credible earthquake and base design earthquake. Then the third important aspect of this code is the resistance and energy dissipation capacity. It's taking care of the nonlinear response, so behavior factors and ductility classifications. So the code limits certain geometries, horizontal and vertical. We cannot use this is very simple, but it's very, very important. We cannot use these code methods for regular buildings, or we have to consider other means to balance by shear walls, by columns, and so on. Detailings are given. Some suggestions that the soil are divided depending on shear wave velocity for the top 30 meters. So we have a classification of 7 different soils. So for that, we have different spectral shapes whose values are determined. Our job was to determine these local parameters. Some dynamic analysis are also done. For a dam, for example, we have found in one dam liquefaction. It is now built. Full dynamic analysis is done, and it is possible. We have tried in Ethiopia. Seismic zoning map looks something like this. Seismic micronization map is prepared for Addis with amplification and period domain. Some structures are analyzed also with dynamic analysis. We can touch. It's not much. This is the dams modeling. Some attempts, but not enough. I think together we can do much. Thanks for your attention. I'm through with my presentation. Sorry for a long presentation.
Thank you, Dr. Masara, for your insightful presentation. Next, we have a special session led by Engineer Carlin Borgas-Sheded, a distinguished structural and earthquake engineer. To see some about her biography, Engineer Carlin is a structural engineer. She holds BSc in civil engineering from University of Surrey from UK, and MSc in earthquake engineering and structural dynamics from Imperial College of Science and Technology, London, UK in 1999. Carlin's career spans several decades, during which she has made significant contribution to help improve seismic resilience of structures in Ghana. She has assisted organization of seminars on earthquake resistance design and served as a resource person. They have also attended conferences and national and international events. These include engineering resilience in disaster risk management of sustainable development in World Federation of Engineering Organization and Peruvian Engineers Association, contributing also in resilience infrastructure system in 2022. And another paper she have wrote is improving earthquake safety of Ghana schools, proceeding of the 16th World Conference on Earthquake Engineering in Santiago, Chile in January 2017. Carlin was a chair in National Earthquake Committee in Ghana that produced the document, a framework for refocusing Ghana earthquake preparedness and response. Carlin is a member of the board of directors in Earthquake Engineering Research Institute, USA, and the Committee on the Disaster Risk Management of the World Federation of Engineering Organization. She is a past president for Ghana Institution of Engineering and past president for Federation of African Engineering Organization, which she was a president when we hold the African Engineering Week in Addis Ababa, Ethiopia. Thank you, Engineer Carlin, and I give the floor to Engineer Carlin. You can share your slide if you have one, and you are now unmuted. Thank you.
Thank you very much for the very kind introduction, and I'd like to recognize the president of FAO, Engineer Refilwe Buthelezi, president of the Ethiopian Association, Engineer Jonas, and my colleague speaker, and all the distinguished participants. Thank you very much for having me. Let me just start my presentation now. I'm going to talk briefly now about basic principles for providing seismic resistance in buildings. And the outline of my lecture, I'll be talking about the response of structures to earthquakes and how they respond, the kind of factors that affect their response, and then common failure moods. Then I will look at some basic design principles. Basically, I want to go through the kinds of things that engineers, architects, and those in practice need to pay attention to when they are
Okay.
doing
Uh,
their buildings.
Are you presenting, sharing the
Yes,
screen? Or?
sorry.
Yeah.
You cannot see my screen.
Yes, yes.
Let me just go back and see.
Yeah.
Okay.
It's not coming yet.
It's coming?
No. It's not. Okay. Yeah, it's coming now. It's coming now.
Okay.
Yeah. For those who are writing on the chat box, we'll have a Q&A session after this presentation in 20 or 30 minutes time. Yeah.
Okay.
We can see it now. Thank you.
Good. So I'm starting with talking about the structural response, of buildings, how they respond to earthquakes, the factors that affect their response, and then some seismic design principles. And I'll look at typical failure modes that have been identified in past earthquakes too. Okay. So if we look at structures and what, how they respond in earthquakes, you find that their response is generally dictated by the level of ground shaking and its characteristics. This may seem obvious, but it comes up with so many different results, unexpected results. So we also need to look at the properties of the structure itself. Now we find that different types of structures subjected to the same level of ground shaking can have very different responses. Sometimes because a structure is short and stiff, it may respond differently from a structure that is tall and flexible. You can also have earthquakes that result in different levels and types of ground shaking at locations within the same vicinity. So in the last lecture, we saw a whole area flattened and only 2 buildings left. All those buildings were in the same vicinity, but somehow there were 2 structures that were left standing. Sometimes it may be a question of topography. You may have structures on hills, on steep slopes, experiencing greater damage than those perhaps in a valley. Those on soft soils may also experience much, much more damage than you expect. And we have had factors like resonance and so on mentioned. So the earthquake waves, as they are released from the Earth's crust, and this is just for completeness, I know we have gone through this, but as they are released from the Earth's crust, they generate waves which propagate through the ground, and as they propagate through the ground, they are affected by the type of path through which they are passing. So if it's a hard, solid rock, it may have one effect, or fractured rock, it may have a different effect. Going towards a hill, it may amplify the motion. And the result is that at ground level, you can experience different types of ground shaking depending on the actual site on which your building is standing. So we say that the ground shaking is a product of the source of the earthquake. We've heard about directional effects, which may have an earthquake, moving more in one direction may have a more profound effect on the structures that are within that path than those that are not so much in its way. So the source matters, the path through which it matters, goes through matters, and the site on which the building stands matters. So this tells us a few things. I mean, if you are designing your structure, your soil report, your geotechnical report is very, very important. And the kinds of things that you need to be looking at will not just be a ground bearing pressure. You'd be looking at matters of the soil, whether you could have amplification, the location of your building, and some of these things are things that may not necessarily appear in a code. For example, uh, putting a building on a steep slope. And so there will be direction, but it may not necessarily be explicitly spelled out. So these are things that engineers really need to pay attention to. If you look at the damage that occurs in buildings following an earthquake, you see that the response is generally determined by factors such as the geometry of the building, the material properties, and the dynamic properties. And it's been found that simple building shapes perform much better than irregular ones. And buildings that are symmetrical in plan and elevation also perform better than those that are not. And you'll see a few examples of buildings. I will show a few as I go on. It seems like it's something simple, basic. Okay, simple buildings do better. But there generally is a tendency amongst professionals to believe that we have all the tools necessary to solve everything. Yes, we do, but it depends on the level of the kind of building you are putting up. Perhaps the effort you put into a high-rise building may not be the same as the effort and money you put into a much smaller low-rise building. And in those buildings, you may want to look at issues of symmetry and shape, geometry, and so on, and try and address those issues. So buildings should have uniform stiffness and plan and elevation to perform better. You need to ensure that you don't have changes in your mass and stiffness in elevation, and you don't have your stiffness and mass coincide. The centers of your stiffness and your mass coincide so that you don't experience torsion in your building. When you look at material properties, the factors that determine how a structure responds include the properties of the materials that are used. So stiffer materials that are resistant to deformation are better. So you would certainly pick concrete over adobe if you were just building a normal traditional adobe building. Strength also counts, so the ability to withstand stress without failure is important. You need damping properties. You need an ability to absorb and dissipate energy. It will be good if you have, that kind of material when you are building, because this reduces the amplitudes of vibration. Ductility is very, very important. And we use materials that have the ability to undergo large plastic deformations. And by plastic deformations, we mean that when that material deforms, it does not return to its elastic state. It does not return to its former state, but it does not break. And this ability alone allows us to build more cost effectively. So one of the things that you would find is that in codes, the steel that is used in construction of reinforced concrete has certain specifications, and those specifications are to ensure that the steel is ductile and can undergo large plastic deformations. Then you have, of course, density. The heavier the material, the more forces it tends to attract. And therefore, maybe a material like concrete would attract more forces than a material like wood. And it's a question of balancing the properties of all the materials so you get the best out of them. And of course, the most important being the material should be able to withstand repeated cycles of loading and unloading without failing. And if you know anything about concrete, it's very brittle. And therefore, when we use concrete in buildings, we have to treat it well so that it's able to perform in a ductile manner, that the structure is able to perform in a ductile manner. So, like I said, stiffer materials may result in stiffer structures, which can attract larger forces. And because the earthquakes are often contain, and this is because earthquakes often contain high frequency components. So this is also one of the reasons why you will have buildings in an area and some will be more damaged than others. In fact, there have been earthquakes in which you would find maybe all the damage was to the shorter structures, shorter, stiffer structures, and the medium heights and taller buildings went away fairly, undamaged. And that was because of the frequency content of the earthquake that the buildings experienced. And although high-strength materials such as steel and reinforced concrete are capable of resisting fairly large forces, their strength alone is insufficient to produce earthquake-resistant structures. You have to treat them right, like I said. You have to ensure for a reinforced concrete, for example, you have to combine the reinforcement and the concrete in a manner that makes the resulting structure ductile, and we'll go through that. Also, low-strength materials you find are not good at resisting ground shaking, and structures must be able to deform and absorb energy without collapse. And so this is what I'd like us to discuss and see how we go about that. The design of earthquake-resistant structures requires a careful selection of the materials so that the resulting structures have the required strength, stiffness, and ability to dampen or dissipate energy, even deform, but not collapse. So let's take a look at the dynamic properties. A structure will naturally tend to vibrate with a particular frequency if it's left to move free of any external forces after it has been disturbed. And we call this the natural frequency, and structures tend to have more than one natural frequency. I mean, they can have more than one natural frequency. And that natural frequency is related to the period of the structure, which is the inverse of the frequency. So a structure will vibrate with different shapes, and these are called the modes of vibration. And depending on the nature of the external force that is imposed, it will exhibit one mode or the other, or a combination of modes. Now, if the frequency of incoming earthquake waves happen to coincide with the natural frequency of the structure, then we have resonance, and we have heard about this in the earlier lecture. But what this does, it really amplifies the effects of the earthquake on the structure and can lead to considerable damage. So in designing a structure, you want to know what its natural frequency is and what the frequency of the earthquakes in that area, the frequency content of the earthquakes in that area. So you can try and design structures that will not end up experiencing resonance. And structures that are subjected to incoming waves with frequencies that are very different will be less impacted. And so that's why you do that. Some structures may absorb and dissipate energy from an earthquake. And this means that the amplitude of their vibrations will reduce over time. And this is a very good property for any structure to have, and we refer to that as the damping ratio. These are all terms and things that you see in your codes, and that's why I go through so that people get a better understanding of what they are doing when they are following their codes. So we have some lessons from past earthquakes, and it's by observing past earthquakes that codes have been, developed and improved to the stage we have now, where I believe that the world is fairly certain that it knows how to design buildings very well for earthquakes. And in some countries, when an earthquake occurs, there'll be very little damage. In fact, the damage may be limited to old buildings and structures that have not yet been built to modern codes. This picture I put here is one of the buildings that exhibits classic failures, which we call soft story failures. You will notice that down we have cars parked, so the stiffness of the building down is not the same as that up. In fact, the building that has a much softer floor down, that's why we call it a soft story, a much weaker floor down. And this may look obvious, but in other cases, it's not so obvious. Where we have shops and so on now, it may not be so obvious that it is a soft story, but the glass windows and so on down do not have the same strength as the concrete or block work above, and therefore you would have soft stories. So these are a few examples of, the kind of problems that have been seen in earthquake after earthquake. And it's good that people are aware of that so that when you are doing your designs, you avoid some of the traps. This was the presidential palace in Haiti. You'll notice above they had long columns that's uninterrupted, and the building below shows what happened. You had this heavy dome roof above which collapsed. The slender columns failed. Good. Another soft story failure, and this time it was in the middle floor, the middle of a building. So probably had glass instead of a similar, thing as the other floors. It may look very nice architecturally, but when you are creating that kind of thing, you should be aware that it is a soft story, and therefore you take extra precaution to put in enough stiff members. And it's one of the reasons why architects should be working with engineers right from the start when they are coming up with a concept. This is a sway mechanism in the ground floor, also a soft story that almost led to collapse, but I'm sure that the building will have to be pulled down in the end. Then you have situations where you have something like this, where elements are completely disconnected from the building. In this case, at the top, you had precast slabs that were not properly tied together to the building. And the slabs, they have an especially important role to play in distributing elements. Unfortunately, in this case, the building lost all its slabs, and the building was left, damaged and standing. Precast slabs need to be properly tied into the existing framework if you are using them. You also have this picture at the bottom, which was a church building in Haiti with the roof blown off, well, not blown off, fallen off, not properly tied. You have situations where you have buildings that are adjacent to each other, too close to each other, and you have what is called pounding. So yes, maybe they were perfectly okay buildings, reasonably well designed, but they were not designed for that pounding. Then you have a situation like this where you had torsion. The center of mass and the center of rigidity did not coincide. So you had twisting, and then otherwise maybe well-designed building then comes down. This has not collapsed yet, but you have a gable wall. I took a picture of this in Ghana. You have a gable wall. If it's not properly tied up the top, it's going to come down. In fact, gable wall failures are one of the very common things. This is not any, this is not something that you would do some sophisticated structural design for, but it can cause failure, it can cause death. Then you have what we call short column failures. So this is a column that was designed, maybe properly designed on the left, but because of the balustrade, which are non-structural, they created a short column there. It's no longer a slender column throughout, and short columns like that attract shear failure. And so you see the concrete all broken and gone. And the same thing on the right-hand side. So you can have these situations sometimes in renovations, and then a block wall is put somewhere halfway, and then there's a window. You have these situations with non-structural blocks being put, and then you create a short column which was not designed, as a short column, and then you have these failures. Staircase failures too are pretty common. In staircases, sometimes you end up with short columns as well because of the landing and the landing beams. And so these are things that need special attention. Beam column joints are especially problematic if they are not properly designed. And in fact, we say in structures that we design for failure. In earthquake resistance design, you're supposed to design so that the failure happens where you determine the failure to be, in the beams and not in the columns. And beam column joints often fail. We'll see a little bit more about why that happens. This is liquefaction failure, when the soil fails, it liquefies. You can have the best design structure and it will still collapse. So you see those structures that have toppled on their side, and they may be perfectly good structures, but their foundations failed. One other failure that happens very often are flat slab failures. Even though there are measures that may be taken to thicken the slab at the column to avoid punching shear, it's a very, very common failure. And in fact, flat slabs is generally, it's better avoid them if you can. Okay, so what do the seismic codes do about this? They provide the engineers with guidelines so that they can design safely. And the codes address specific requirements for load-resistant structures. And you have the codes, so they would have something for steel moment-resistive frames, steel braced frames, reinforced concrete moment-resistive frames, and so on. You will find out that load-resistant elements must be adequate in number. Penalties will be applied for structures that are irregular in geometry, mass, stiffness, and so on. The penalties usually meaning that you need a more stringent analysis of the structure. Then with steel structures, you need to pay attention to your connections. You may need high strength bolts and welds, which you need to design. Steel generally performs quite well. I mean, it's ductile, but you may need to brace it so that it doesn't deform too much, and it helps to ensure its stability. with reinforced concrete, you need to pay attention to detailing. This is not something that people consider very exciting. It's not design, it's not calculations, but it's so important. You need proper detailing of your hooks, bends, laps, and so on. And you need to pay special attention to the joints. We've seen how joints tend to fail in earthquakes. So the moment-resistant frames must ensure that you have a ductile structure. Usually the links in your reinforced concrete is what will help you to confine your concrete and ensure that your concrete members behave in a ductile manner. You can add reinforced concrete walls and shear wall systems, but they must also be very properly detailed. And I believe I have a diagram later. So when you are designing your moment-resisting frames in reinforced concrete, you do your design, get your results, but like I said before, you are to design for failure, and you want the failure to occur in the beams. So you need to do what we call a frame that has a strong column and weak beam. And to do that, after you've done your design, you then check and see the capacity of your columns and see if they've got a greater capacity, moment capacity than your beam. If they don't, you increase your column size or your reinforcement size, or do whatever it takes to make sure that your column becomes stronger than your beam. So the tendency is to have columns that are also bigger than the beams in seismic design. So this is just a diagram of showing, where the yellow dots show you where the failure should be. And this is showing you about detailing. This is so important. The links that you put in and the way you bend the links. In the past, we were bending links at 90 degrees, but no more. It's now 45 degrees, so it's well locked into the concrete and does not come out when there's strong ground shaking. It should also have sufficient, laps and so on at your joints, and you lap in the right positions. So these are all specified in your codes. When you come to detailing at the joints, don't bend bars through your column. Allow your column links to go through without interruption, and let the beam bars pass straight through the column. This, of course, means that your beam will have to be smaller than your column. And this is also why it's good to start the conceptual design with your architect. When it comes to reinforced concrete walls, you should have boundary elements. So you have like columns at the ends, which may be bigger or the same size, but they should be well detailed. You also have closely spaced links and so on. And all these are specified in codes. That it comes to foundations, you should try and rest your foundations on the same horizontal level. So if you have putting up a building on a slope, you can interconnect the foundations with a grid of beams so that your foundations move together. Or you can use a mat. In these diagrams I have here, you see that where they wanted, where they had a slope, they provided a rigid base throughout. You can also separate the structures so that you have two separate structures, and then each one can be on its own foundation. So these are just some of the things you can do to ensure that you have the right kind of performance. Then, of course, when it comes to distributing mass and stiffness, you try and put your shear walls and so on around so that in a uniform manner, so that your stiffness or your mass coincide. So this requires some, effort ensuring that stiffness and mass coincide. It's not easily done with software. So to conclude, the seismic performance of buildings depends to a very large extent on the building configuration, and engineers and architects must be working together at conception stage, else the structure can become difficult and expensive to design. If you choose the building configuration that permits structural simplicity, you reduce the uncertainties in the modeling, and you can have a more reliable prediction of behavior and hence design. And then if you provide adequate load resisting elements, they will then be able to resist your horizontal loads as well as your vertical loads. Then you must also secure the connections between all elements of the structure. So beams, columns, they must be properly secured to one another. The whole idea in earthquake resistant design is to get your structure to move together and not one part moving at a different pace from the other. In reinforced concrete buildings that have more than one story, use rigid slabs to connect all your vertical load-bearing elements. And this will help preserve the shape of the structure. You must also ensure that there's no interference from adjacent structures or non-structural elements. And then use good quality construction materials and good building practices. Good seismic design is good construction, good design. So you can't go wrong. And then you must also ensure your foundations, you have firm foundations, you have no abrupt changes in your building plan or stiffness, and you separate adjacent buildings so that you avoid pounding. And of course, you should avoid the short columns and flat slabs. So thank you very much. This is in conclusion what I want to talk about. And let me just add that although I have been speaking about buildings, the same principles go for any seismic resistant design. If it's pipe work or so, you may want to put in flexible joints so that they can move, continue to move together without any breaking. So thank you very much for your attention. I think my time is up.
Thank you, Engineer Shedid. Yes, it's a very good timing. Almost as planned, 30 minutes. Thank you very much. So now we are on a comment for our renowned experts in earthquake engineering. If you have any geotechnical earthquake or any general question related to earthquake, you are welcome. You can unmute yourself or raise your hand first and unmute yourself in the video and you can ask questions. The floor is open to the participant and feel free to speak of your mind. Also for language, we prefer English, but if you prefer to speak in Amharic, you can do that too. So the floor is yours. If anybody have a question, please raise your hands and you can ask or comment or add to the presentations. Anybody? I think I see a hand. Engineer Abisalom, did you raise your hand? You can ask us a question. Yes, Engineer Etabezao, you can ask questions. You can unmute yourself. Yeah. Yes, you can.
Okay. Thank you very much.
Mhm.
Can you see? Thank you very much for the good presentation for all the presenters. I have two questions. So the first is for Dr. Messele. So why are we having more frequent earthquakes recently in Ethiopia? Is it because they are more apparent and we are registering and communicating them more? Or is it a human factor that is causing them? So that's my question for Dr. Messele. And my question for the second presenter is, I work in the roads authority, so we are worried about bridges. Currently, there is more frequent earthquakes in our country, and it is destroying some of our roads and bridge structures. So do you have any recommendation in terms of the material we should use or design consideration that we should make? Thank you very much.
Thank you, Engineer. Engineer Tabazo, thank you. Yeah. You can also write your question on the chat box if you are shy, but we encourage everyone to and open your video. Dr. Masala, you can address the first question. Yeah. Let's do it one by one. Let's do it one by one. Dr. Masala, yeah, unmute. Okay, okay. Let me unmute you. Yeah, you are unmuted. Dr. Masala.
Should I continue? Okay.
Yeah.
The recent earthquakes occur, they don't occur all the time. It requires, of course, earthquake prediction is not a science yet. No scientific research has come to a level of predicting earthquakes. In 1976, they did in China from animals' behavior, but scientific method is only short-term prediction. Like Tokyo, they have a lot of instrumentation. They may see animals before it comes. But for now, let's say it's not a science in terms of prayer, but there is a pattern. There is a probabilistic seismic hazard analysis. And this shows that energy in some area is dissipated. An earthquake means an energy. It is like the buildings. The earth is suffering to carry more stress than it strengthens. So when that is passed, it either snaps in convergence zones or pass one another sliding in transform, or in our zone, for example, like in the rift system or in ocean, it separates. This is the energy release mechanism. So elastic rebound theory assumes that energy is released and it comes, let's say, to zero. It's not zero, but let's, for practical purpose, consider zero strain develop, means zero stress level. Then it accumulates over years, then it releases again. For example, in East Africa Rift system, there are earthquakes occurring every about 8 years, repeatedly. But this one, for example, there was similar earthquake in 2005. So now, after nearly 20 years, similar phenomena occurred. By the way, the Earth is in dynamic equilibrium. The tensile stretching we have at oceanic ridge, or like in East Africa or in Iceland, is balanced elsewhere. So as you have seen, the earthquake is now occurring in California, in China, in Asia, because the world is one. It is in one dynamic equilibrium. So this movement occurs certain times. Just going back, 1906, it was San Francisco. The Ethiopia 6.8 occurred 1906. There was earthquake in India, Indonesia. The 1964, which Madam showed, the liquefaction in Niigata, 1964, 7.2. In Anchorage, Alaska, a 9.2 earthquake occurred. Then it is again the same. 1989, 1994, 95. So now also the earthquake. So this is, you know about the Earth, this is something like 6,370 in radius. We don't know the whole phenomena, but understanding from the earthquake tectonics, energy is accumulated, and when it gets a chance, it releases. When it releases, it in sequences. But this one is a little too much, too many, is more than the human activity. I'm feeling the Earth has ruptured n times, more times than before. This Rift Valley is a weak formation. It's not very strong. It is the lithosphere is very thin, and it is a more sediment filled because tensile stretching. So at every earthquake, it is getting weaker and weaker so that we have much release. But there is a research ongoing. The scientists will explain more. Mine is like a guess. But personally, I'm happy energy is released with these 4.85 earthquakes because we'll have another chance until it accumulates another. It's the worst is we actually call it seismic gap. When an earthquake didn't occur in an area for a long time, we're more worried. But please don't take it exactly literally. We can be surprised by 6.8 or 7 somehow, but theoretically the energy is released. So this is how it is a pattern. It's a statistical. It repeats after accumulating energy.
Thank you, Doctor.
Earthquake is very strong. Like the 5.8 is if you consider in TNT, it is something like 50 million kilo of TNT, the 5.8 that occurred earlier. Human cannot influence such type of energy. The sixth earthquake is 63 billion kilo of TNT. So please understand human influence on seismic is almost impossible.
Thank you, Dr. Masara, for addressing this very critical issue that humans cannot interfere with earthquake or the seismic zone. In addition to her question, I need, Madam Carlin, there is a question from Asfaw. Is there any consideration during the design of seismic effects for the roads and airport runway pavements in addition to building infrastructure? Please add this into your answer. Thank you.
Yes, thank you very much. So the question about roads and airports and bridges. So for the bridges, it's the same principles. You need to have ductile structures. But I would also add, if where possible, build in redundancy so that if you lose any supporting members, there are others to, help carry your structure. Bridges are so important. They may be needed in an emergency, in an earthquake, and so on. They are the kind of structures we don't want to fail. So for bridges, you build in redundancy if you can. You add dampers if you can to dampen vibrations, and you sure and all the other things that we've spoken about for the structures having ductility and so on also apply. The other thing is in construction of the bridges, the bridge deck, the supporting members, there are ways of detailing. I don't know the technical term. I'm not a bridges person, but you see that some bridges, they have sides, a U-shaped channel supporting the bridge deck, so that if there was any shaking, that bridge deck would not fall off. And then you have some bridges that are just sitting on like a pad, and you can just imagine that that one, it looks like it's just designed for vertical loads only. And you can imagine that if there was any shaking, the bridge deck could fall off. So those are the kinds of things that you should be looking at in bridge design. With the roads, earthquake pavements, and so on, I believe it's a question of your soil and paying attention to the soils and the site, ensuring that they are well compacted and so on. You don't want liquefiable soils underneath your earthquake pavements. And so whatever you need to do to ensure that you don't have liquefiable soils or soft soils, you should do it. I believe it is a question of good pavement design. And that should take care of any earthquakes. Thank you. Have I missed any question?
No, you have addressed them all. I have a couple of questions for Dr. Masala from the chat box. One is from Engineer 100. He's saying for high important buildings in Addis like Black Lion Hospital, build under older codes with minimal downtime tolerance. What strategies enhance earthquake resilience? Could rapid visual screening RVS FEMA help quick assess retrofit needs? Are there any institutional or governmental programs aiming to address such risks? Another question is from Engineer Jonathan. We have seismic building codes in Ethiopia. We have seismic building codes in Ethiopia, but enforcing them isn't always easy. What do you think are the biggest challenges in making sure buildings actually follow these codes, and what practical steps can be taken to improve enforcement? Dr. Mr. Ipan Country, unmute. Yeah. Unmute. Dr. Mr. Unmute it. You can unmute it, Dr. Mr.
Okay.
Yeah, okay.
Thank you very much. For the retrofitting, some important structures, good enough, by the way, just now we are revising the seismic code of Ethiopia. A committee is formed. So in terms of seismic, previously we have two, the soil property testing, which is associated with geotechnical. And we have, you remember the ESB, Ethiopian Standards 8. This is general and seismic actions. But now we have separate for building, which is 8.2. 8.3 is for breeze. 8.3 is for assessment and retrofitting. 8.4 is for silos, tanks, and so on. 8.5 is for foundations, retaining structures, underground structures, and so on. So the current revision of the code is more expanded to include this, including retrofitting or breeze and so on, underground structures. But I think it will take about a year. We just started now, but we expect better. What do we do? Except for the code, retrofitting, there are, let's say, two conditions. The first one is before an earthquake occurs, we have to delineate buildings and study. I think we're too afraid to touch that uncharted territory because we did not, even the course we have, Ethiopia has a course since 77, CP 77, then 83, then 95, many years. But first of all, the old course didn't have good considerations, for example, in terms of ductility, in terms of even stiffness, in terms of detailing, they said nothing. Even what we have now, it has, code is, by the way, let's say like this, the code is, the code says, in the absence of scientifically or more rigorously designing, you use a code. Code is a law which averages some consideration. So if you can, let's design, by the way, capacity design, Madam expressly, design and redesign, check the capacity of the code, which is very easy. Do more, let's involve as engineers more and more in more actual capacity design. The deformations, let's see if they are within elastic or in the inelastic, they deform in the ductility. So what I'm saying is code is very much average. And another opinion is it is force-based mainly. The good thing is that the elastic response spectrum or some models, even for structures, nonlinear models, if we can include that and check your joints especially, that is good. Okay, now most of the, so don't be comfortable with the current code also. Code is really an average for people like me who are lazy. If possible, make dynamic analysis. There's softwares now. It's not that difficult. We can catch different modes. For one building, we have 28 model participation. I cannot mention the name because we did for a company. It is a 40-story building, irregular. We have nearly 40 mode participation. Can you imagine? With the code, you have model participation very much with often one. So just compare with this model participation, which Madam also made. Thank you, Madam, by the way. It was very insightful. You touched most of the story. So now, whatever we design with current code, let's not feel safe, but the old ones are worst. Is first, the codes are limited, whichever code. Then second, it requires detailing. The beam passing this reinforcement through the column through the beam looks very simple, but the column, the joints fail first all the time. Their energy displays, we leave them empty, they fail. There is no ductility there. This stirrup bending looks very simple, but the open ones fail first with the cover. Then they open. Imagine, go now with current code. I can see 100 sites, you will get 50, 60 as well. People don't bend, very simple thing. The spacing of stirrups near joints. So code is that limited, let alone so we have to retrofit. We have to choose. If possible, we have to evaluate all buildings. Important buildings like hospitals. Sometimes churches, mosques, where people take this is a rat from God that has destroyed. It could mistake it is like some acropolistic date and so or day or so. Where, for example, what happens if the council or minister in one country fails while they're making meeting? It could be a failure of the system. It could be a riot, a coup d'etat, anything. So we have to differentiate the schools. So we have to retrofit. It's very easy. It's not that difficult, by the way. Actually, previously mentioned resonance. If our building is in soft soil, we add frames outside. We retrofit them. We make them strong. If our soil is very rigid, we may reduce short columns, soft stories. Most of them are known, by the way. Long known theories, and from the pictures you can see this in Kobe, everywhere, Northridge, Loma. So we can retrofit buildings, and we must for some building. For example, you consider like Black Line. For example, if I'm the mayor of the city or I have the authority, I'll choose two hospitals at least and retrofit them. What happens in an event of an earthquake even? Where do we go? We don't know. We run to this hospital, it is broken, it has failed. So every country must have a strategy for earthquake response by retrofitting support structure. If possible, let's retrofit all, because the damage is not easy. It could be like 230,000 people died, and the city is nearly destroyed. So which one is cheaper to retrofit? And most countries did that. In LA, they did that. In Japan, in many places in earthquake-prone areas, they did that. So Black Line, I have no specific prejudice against, but it is very important hospital in the city. At least it should be retrofitted. Many things like that also.
Thank you, Dr. Masala. I see a hand from Engineer Sophia, Academic Chair. You can unmute and ask question.
Hello. Can I be heard?
Yes, yes.
Yes. So good afternoon from Ghana. And I'm so happy that we had this webinar. And thank you to Dr. Meseli and Madam Carlin. We've really enjoyed the presentation. As engineers, we are responsible for the safety of the public. And since the discussions that we are having borders on public safety, I would like each of the presenters, if they can, I know they can, to talk to me as somebody who is not an expert. So give a message to the general public, that is one, and also a key message to the city authorities. What would be their key message to the city authorities, and to the general, to the public as well? So that would be my question for each of the presenters. Thank you.
Thank you. Madam Carlin, you can proceed. And then Dr. Masala.
Thank you. So just before I answer those questions, I just wanted to make a comment on enforcing codes, and perhaps it will also go into my answer to Sophia. That when it comes to enforcing codes, it's not an easy thing. we all have a responsibility. And I think that city authorities can help a lot. It is, first of all, you tackle the ones that are easy, public buildings and so on. You make it a requirement that they should be built to code. They should be audited regularly, every 5 years or so. And if there are any renovations, they should use that to upgrade. And then when they've done that, put a public notice to show this building has been audited. Who wants this building has been designed safely and has been audited. So when you do that for public buildings and people become aware, developers, people wanting to rent those public spaces and so on will start asking those questions. Nobody wants to stay in a building that is not safe. Therefore, they will start asking, and then it will gradually filter down to the rest. So start with the public buildings. And so that will be my message to the city authorities, start requiring public buildings to be designed and to be audited and to show that they are been properly designed. The second thing I'd like to say is that when it comes to rapid visual screening, I learned this recently. There is a method that was used in Turkey and tested in Haiti and tested in Turkey again, which seems to be a pretty good method for checking the likely performance of a building in an earthquake. And it's much simpler than the other FEMA methods and so on. And it gave excellent results. In fact, so good that in Turkey, they did say at the last World Conference, they were going to incorporate it into their codes. So it might be useful to know that. The final thing I want to say is that we should not forget insurance. When there's a disaster, somebody has to pay. The first thing I learned was that in the West, when there's a disaster, we in Africa and all of us help to pay for their disasters because they insure and we don't insure. So we need to bring in the insurance industry as well, and they may also help to enforce compliance because they may not insure your building if it wasn't properly designed. Thank you.
Thank you, Madam Khalil. Doctor, you can proceed.
From your question, I cannot take you as a layperson. You are somehow learned and knows well for your modesty, great. However, for the general public, let's say who is here and not, if we somehow, as authority in government or in private company or our own houses, we should consider employing, if possible, an expert, if not an engineer, because this is not very complicated things. For example, soft first story, we can consider jacketing by columns and increase the capacity of the columns. They fail because they're long and they don't have this, they have the soft spots. Short columns, separating walls from columns, just adding like styrofoam or other softer material between like walls and column will avoid that short column effect. So there are many things. If we have a flat slab, adding some pedestals. We have done many retrofitting works in Addis for some buildings. It's not as complicated as you may think. So such type of things we can help with that. The other is the personal care and our family matters. When an earthquake comes, we really have to have preparedness. These simple techniques, staying under a table or a bed, under door frame, and not running away when the earthquake is shaking, because you will be hit by something you can't escape. Stay where you are, try to avoid many things. So small details are helpful for the public, and some preparedness, have flashlight, put off fire and so on. You can save your family, yourself at least. For the government, public, let's say, public has a lot to do. So what I can add isn't much, we have to evaluate all our buildings. By the way, it's not that difficult. It does not require an expert. When an earthquake happens, we always go there. I've been to many earthquake sites when I was a student, especially. Now it's not that easy to travel from Ethiopia. But, you know, students, engineering students are trained, let's say with FEMA manual or with the American Society of Structural Engineers manual. You go, it is like, what is a crack type? You have a training. You can, the immediate assessment will be done by like one professor or one senior engineer leading hundreds of students. Then we can evaluate this quick assessment. And label the buildings, for example, red, green, yellow. Red means no entry, means column failure, and so on and so on. Some beam cracks and so on, limited entry. If it is some superficial, it is wall and so on. You can have, even you can reside in it for a while, just watch for aftershocks. So site type of classifications is one, quick assessment. The second is a detailed assessment. This is also based on training. So the buildings, the FEMA is good, but mainly it is after post-earthquake, strong post-earthquake, that before that, the other manuals, ATC are good manual before, the Californian chapter of Civil Engineers are good manual. In Japan, the Earthquake Engineer Association even has a manual. So site type of manuals. Then what now? With this effort, with Federation of African Engineers Organization and Ethiopian, Ghanaian, and so on, we can come together. We're always looking to the West, so we can prepare really some simple manuals in our respective fields and then use it. Because we know our buildings, the buildings are very much similar in Africa. The quality, the economy, some variation, but they're the same. So if we work together, we can produce such type of things. It is not like a nuclear physics. Earthquake has been there. It is like energy dissipation, it is strength. So the FEMA is good, but we can adapt. There are more practical manuals to do that. So the public, this is expected. Often the problem of the earthquake is like in Ethiopia now, where many activities from government and so on were called here and there. Then an earthquake dissipates like attenuation with distance. After further from the earthquake, it is forgotten first by the public, the government, then even the experts. We can't do much. So this initiative could be one effort that we can do in Africa, as if not a basic research, because the basic research are done, but to adapt this existing research for practical use can be one way. I'm just encouraging, or it's a plea.
Thank you, Dr. Masala. I see lots of questions in the chat box, and most of them have been addressed. And if anyone wants to ask a question, you can raise your hand. There is still time, but I see only one question that is different, and it is about Tandaho Dam from Engineer Abisalom. He's saying if the dam fails to downstream area, is there any, I think he's trying to ask, is there any assessment that has been initiated now to address any critical failure on the dam? I think this one is directed to Dr. Masala. Yeah.
The Tandaho, more so the Kasam Dam, are unfortunately built very close to a fault. I'm afraid some faults are not always seen. Sometimes they're seen on ground, sometimes they are blind faults. So it is expected that these two dams are not at good location, very close to the fault, and they can even be intercepted by a fault, a possibility. So that could be found out by geophysical survey through geoseismic or geoelectric or gravity anomaly. So this is the first thing to do, is to check the surrounding area for active faults, because no structure could be saved against a fault. It's a lot of energy. The second is actually, I did the stability analysis for the dams. The picture I showed earlier is these two dams. The stability and so on and so on, it has been designed for 2G, 2 times gravity, may not be a big issue. But the method of construction, the compaction and so on, I didn't know. So it could be at risk. So one way is when there is a big seismic activity, that's why we have the under sluice. We have to let out water and reduce the size of the water and reduce the static force and the hydrodynamic force. That is what is done in most responsible way for dams when the activity is more. But we have to reassess, and we can strengthen by this. These dams are earth rock fill dams. They can be strengthened easily after the assessment. And now I have known that some committee is formed under the Ministry of Water Resources, and some assessment is going on.
Thank you, Dr. Messele. Madam Kalin, do you want to add more, or if anybody have a question? Okay. Okay. So another question I have is from YouTube. Why is most of the earthquakes are happening on the eastern part of Ethiopia? Why not in the other area of the Rift Valley? Yeah, you can address this one, Dr. Masala. Again.
Unfortunately, we don't choose the earthquake, they choose us. It's earthquake. It's a fault. The fault in the system is the main cause for our earthquake, and it is in the eastern side, or it starts from northeast. And actually, when we go to the south, like the Arba Metrosana area, they come a little to the west also. So this is one a reason it is very active fault. But let's not eliminate the possibility of a blind fault that can surprise us. For example, the Juba earthquake, which was 7.2, is not expected to have that type of earthquake in the interior of Africa. Some big earthquake occurred in Central Africa and in South Sudan. So let's not eliminate, of course, like the western part of Ethiopia, especially west north, is a zero zone in our code. But for important structures like the GERD, like some important high-rise building, we have to always consider. It has happened in India. I think it was in 1993. An earthquake occurred in zero zone and caused a lot of damage. So our knowledge of earthquake is after it occurred. We map after it occurred. We don't know before it occurred. Kobe in 1995, the Hyogo-Kennan earthquake. Kobe was the least expected area. More preparation was for the Kansai area, Tokyo area, and so on, but it occurred in ironically under the city itself. So yes, we have more earthquakes there, but the zero zone, yeah, zero statistically. But it is how many return periods we took. If you take 2,000 years of return period, we have data somehow, you will find earthquake everywhere in Africa. It is just a return period. It's a limitation of the statistics and data. So, but for reason, the earthquake concentrate around faults, and they have appeared and they reappeared and they reappeared. We don't have to lose sleep, but for very important structures, we have to consider minimum of safety.
Okay, thank you. Engineer Mohammed Hassan, can you ask the question? Can you unmute yourself and ask your question? I couldn't understand your question on the chat box. Mohammed Hassan. Okay. I have another question from Aidan. What shall we do if earthquake happens in Addis, and what is your recommendation for instant reaction? Madam Karin, can you address this?
Instant reaction is if you are in a building, stay where you are and look around. Because okay. Like this, an earthquake, the recent earthquake are 3-4 seconds issue. Let's even 8 seconds. We
Yes.
cannot outrun that. We cannot outrun an earthquake. It's very fast. So let's stay where you are, watch around, and see if something is falling or not. If we have a chance, like I'm sitting now in front of a table, I'll go under the table, bed, or anything that gives us space. Door frames are also good, but stay away from windows. Usually, the inner side of a building is safer as compared with outside because there are more columns and more if the shear wall or structures are around the center and they support each other. The outside, they have the tendency to fall, windows shatter. So choose the inside part rather than the outside part. This second, if we don't have anywhere to hide, even a door frame opening and staying under it is good. If not, I think with the minimum knowledge, stay under beams and in column areas rather than an open slab because we expect more strength. If it is a good design, the column is not even supposed to fail. Mechanism has to be created in the beams. Then, and don't also panic. For example, there's many earthquakes now. I did not move a single minute. I was in Japan for 7 years facing a lot of big earthquakes. So start to panic when something starts to fall, not for shaking. When lighting fixtures swing, when glass starts to fall off shelves, books fall. For some movement, it is okay. You don't have to. So when something starts to fall, that's the time it is a trigger time. Or when we hear a sound, not of corrugated iron sheets and so on, but walls cracking and so on. That type of sound is the level when we panic and we start to take that action. Then once this has happened, when it is finished, there is nothing falling sound or cracking sound. That is the time we should go out. Even that time, be careful because some things that is weak, walls could fall to the outside. But inside is better than outside. If we are at the ground floor just by the door, if you go outside, please run away from the building as much as possible because buildings usually fall to the outside. That is the care we should take. If there is a fire, even for smaller sway, put off the fire because fires kill more people in Kobe than buildings or building collapse. The fires consume many people. In San Francisco, 1906, 1961, fires consumed many, many people. So put off that is the care. So, but when we with the trigger for panicking is falling of objects, sounds of falling objects from other places, prefer inside than outside for the time being and go out. Because if they, for example, sometimes an earthquake occurs 6.1 and aftershock is 5.8 immediately. So the building that is already weakened by the 6.2 can fail under the 5.9. That's why you should use the small time you have to evacuate the building if it is a strong one.
Okay, thank you. Madam Karin, do you want to add on this? I think Eden questioned the right question.
I think it's been answered perfectly.
Yes.
Go under the table and at the first opportunity, get out of the building and stay far from the building. I think I couldn't have answered it better.
Okay. Okay. So if I see already most of the questions are just being repeated. So we have like 10 minutes. So the last question is from Asfo again. Do you think the Kasam Dam was constructed at appropriate location with regard to high seismic area as seen today? I don't know if you have to answer this one or if we move on to the next question. Doctor.
No, it's okay, but really we're in the academics with teachers is not a good place. But we cannot avoid all the places because of earthquake. We have to design better. That is so. If not, for example, we evacuate most of Japan, for example, Tokyo, Kansai, Nara, Kobe. We have to live with earthquake. The difference, the example I gave earlier is the 2011 in Christchurch and Haiti. Why 7.2 earthquake? has that difference, hundreds of thousand differences in life. It is how we build. So we can build in Kasam or in Tandao. The only thing we should avoid is the faults. We don't build on active faults because there is no worldly way to overcome a fault. It is too much energy. By the way, the atomic bomb of Hiroshima is like in the order of 5, the whole energy. So imagine 6 means it is logarithmic scale. By the way, so it is 31.7 times more energy between one scale. So imagine a 6 earthquake, which is about 32 times more strong than the Hiroshima bomb. So you have no worldly means to avoid a fault movement. It is a big strain, not only the stress, the shaking. It is a big strain. So let's avoid the fault areas. Some methods exist, though, to make a sliding dam, but I don't believe that is a very good way. Some people design concrete sliding blocking, which slides it is on a fault, but let's avoid. But for the Kasam Dam, it is already built. So it is the action now is to make a good geophysical survey and see if there is an active fault close by. The active faults could also be determined, at least even from history, at least, if not by dating. Carbon dating is one method to know an active fault or not, because we don't know. An active fault is a fault that was active in 1,000 years' time. So almost what happened 300 years ago. The second is we can strengthen, at least for public safety, that it wouldn't fail. Even if there is fault, we can live with a crack that propagates slowly. But we can take a measure so that we strengthen, and even if the crack passes by it as a fault, we have to take care of the flowing water by creating a diversion. If there is a city center, if there is a population center, we can create a channel to divert any flow. So that's why we don't have to be afraid to mention in the wrong or in the right place. We can mitigate. We have solutions.
Okay, yeah. In addition to that, I have this one question which is pretty much similar. Does the geological condition of Ethiopia, like some of the part of Ethiopia is mountainous, does it have any effect on the seismic activity?
The geology.
The geological difference.
Madam explained earlier site effect. Locally, the sites can amplify up to 3-4 times, but often two. Because of the damping. Soil has a damping process. Soft soils are the ones that amplify, but they have the damping. Damping could be, we consider 5, but the soft soils could go much more than that when the strain is higher. For example, strain goes to 10%, strain goes to 8%, the damping can be higher. So the local geology, the soil, the geotechnical, has an effect that's very clear. But the geology has effect. Actually, we get enough time. The topographic effect. When you have a topography, like a ridge or a slope, then it is a concentration of energy. The waves travel anyways. So when they come to a ridge type of topography, the body waves and the surface waves and body waves coming from 2 directions coincide, and there is what we call topographic effects. Even the geomorphology has an effect. The geology, if we have rock, let's assume between Tandaho and here, we have rock. So, or soil. If we have rock, the high frequencies arrive here, the low frequencies are damped. If you have soil, the high frequencies are damped, and this is about the attenuation. I'm talking about the attenuation. Then, the damping property, the geology is one of the factors. Actually, the seismotectonic theory is also broadly a geology. It is a plate tectonics. A geology is a bigger crustal continental issue.
Thank you, Dr. Messale. So we are about to end our session. We have only 10 minutes. So, Madam Carlin, if you have anything to add, or Dr. Messale, now is the time. Yeah.
I give to Madam.
Okay.
Unless she can say more.
Okay.
Okay, I don't have too much to add. I saw someone that has asked something about performance based design. I just wanted to say that we are also going to start looking at our code in Ghana. And one of the things that has come up in when you come to look at earthquake codes is that we, in the past, were all designing for life safety only. It is now, so our buildings are meant not to collapse in the really big earthquake, but they may be so damaged that you will have to replace them. And we'll consider that a good design. So we now realize that there needs to be a lot more consultation and discussion and perhaps options being given so that builders and developers have the option to do something that is more than just life safety. And so, as I saw the question about performance-based design, I said maybe that it's time we start incorporating some of those ideas into our codes so that people have a choice to put up structures that will perform better. Thank you.
Thank you. Thank you. Anything, Dr. Masala, before I pass it on to the leaders?
The Federation of African Engineers Organizations, the civil engineering, and especially to the leaders, and also to Emmanuel, who is very diligent, young, and I really wish you big success in your profession. You are a good organizer and consistent. When young persons like you, we can think of our retirement.
Okay. Yeah, thank you. Thank you. If our leaders, our distinguished leaders, Engineer Jonas and Engineer Refill, if you want something or before we conclude it, yes, it's not the time.
Thank you so much. As I was listening to all the conversations, and I've also posted about these conversations on my WhatsApp, the amount of interest in these topics is really unbelievable. And this just shows me that, Emmanuel, we might have to have another 2.0 conversation, because these are true matters that are affecting us on a day-to-day. And some of the questions that the panel members have been answering, you could see from the questions that there's also fear of the unknown. And I'm very happy about some of the responses, because whilst we may not necessarily be able to alleviate the fear altogether, but we are working towards bringing the necessary tools that every single person who goes through a particular event such as this will know what to do. And I do think it is really our duty to take that further and to provide some sort of a document that guides everybody as to what do you do when the event starts to happen. And I think we will take it upon ourselves. We will have a conversation with Emmanuel and the team, with Dr. Masela and Engineer Kalyan, and many more experts who've been responding to my messages saying, please, next time invite me. I would like to be part of the conversation. I do think we need to play a huge part in assisting alleviate these challenges. We might not do anything about it, but we might find a way of protecting ourselves from it. So thank you so much for the conversations. Thank you so much for the contributions to both our experts, the amount of questions that you had, the notes that I took. Dr. Masele, I think we will be coming back to you soon as FAO. Engineer Kalyan, I think our work is cut out for us. We do need to do something to assist in some of these areas. I had a great time. Thank you for inviting me, and I look forward to many more conversations such as this. To yourself, Emmanuel, and to Sophia and the team that has been assisting us with this, I think you've done a great job, and I look forward to having a lot more of these webinars. Emmanuel, I think you said you're giving me 3 months. I don't know if that's enough, but you did so well. We might need more of your time. But thank you so much.
Thank you. Thank you. Okay, thank you, Engineer Refil. Engineer Jonas, if you want to add something.
Thank you so much. Thank you, everyone. Thank you, Dr. Masala and Engineer Khalil. I really want to appreciate our President, Raffaele, Engineer Raffaele. I hope we'll have a good time in the future on other topics. But I really appreciate Dr. Masala because he had been really trying his best to introduce and give a good direction on seismic and also engineering aspects. Basically, there are so many questions that can be raised by different professionals. It's not the first time that he was taking the floor. There were 2-3 programs that were focused on this area. And I hope Ethiopia can use him, and also we can extend his experience to Africa. He's a well-experienced engineer on seismic engineering, and we will have a lot to learn from him also. I really wanted to appreciate Engineer Kalin, our previous president. I'm happy to see you here in this online event. Engineer Rafaele will meet on your program, and we'll have our own program there. We'll discuss a lot on different issues. So we'll have different programs in the future. Maybe we will arrange a special program arranged by the association together with FEO. So we'll discuss the details in the future. Thank you, everyone, for your participation. And thank you, Emmanuel, for handling all these issues. Thank you. Thank you so much. Have a good night.
Yeah, without further ado, let's everyone open up our videos, and we will capture our photos. So everyone, please open your videos, and we'll capture our photos by saying thank you, FOU.
Thank you very much.
Thank you.
Yeah, thank you.
Thank you.
Yeah, just keep waving. I didn't take it yet. Let's put it. Yeah, okay, gallery.
Thank you very much.
If anybody help me capture the photos, just yeah.
Thank you very
much. I only see some 20 people. Yeah. Okay. Yes.
Thank you very much. Thank you.
Thank you.
Thank you.
Thank you, Arman.
Okay.
Thank you. Good night.
See you next time.
Thank you. See you. Bye-bye.
Bye.
Thank you. Thank you.
Bye-bye.
Engineer Zalalam. Yeah, you are unmuted, Engineer Zalalam. Unmute yourself. Okay. Thank you, Madam Carlene.
Thank you too. Well done.
Thank you.
Yes. Have a nice time.